This is homework 2, part A. So to start, I will derive the three-dimensional heat diffusion equation for Cartesian coordinates using volumetric flow rate or volumetric heat generation. So if we imagine a cube with this as the z-axis and a length of dz, this as the x-axis, length dx, and then y-axis, length dy. And the cube has a stored energy. So we'll call that E stored, which is equal to our change in temperature with respect to time multiplied by our density and our heat capacity throughout our area, which we'll call dx, dy, dz. Now the cube also has energy generated. Which will be equal to our net heat flow throughout our area. So that would also be dx, dy, dz. Okay. So, using this, we'll get an equation that will say that our stored energy is equal to our net heat flow plus our generated energy. Okay, so our net heat flow will be the net heat flow of the x direction plus net heat flow of the y plus net heat flow of the z. Okay, and then so like, for example, starting with the net heat flow of the x direction, that's what we'll find first. So in order to do this, we know that the net heat flow in our x direction should be the heat flow of our x minus heat flow of our dx. So effectively that is in minus out. So in order to proceed, we should put our dx in terms of our x. So to relate those two, we need to do a Taylor series expansion. So if we draw a coordinate system here with a curve of f, and say we have value x here, and we know that the slope at x would be this. So the change of our curve f with respect to position. If we have another value, we'll call dx here, how can we find the slope of our dx? If we use linearization here, we can evaluate the slope of our dx using the slope of our x with respect of our dx equal to that slope of our x. So if we write this out, so to find the net heat flow of our x direction, we'll get this equation. We'll say heat flow of our dx is equal to the heat flow in the x direction minus the temperature gradient, or heat, because this is just the slope of our heat function with respect to position at dx equals x multiplied by our change of position. So dx minus x. Okay. So simplifying this, we'll move this x over here. So we'll get qx minus qx minus our change in heat flow over change of position, evaluated at dx equals x, multiplied by our dx. So these two will cancel, and we'll be left with our change in heat flow, negative, over change of position, evaluated at dx equals x times dx. Which can simplify down even further to heat flow dx is equal to our our change in heat flow of the x direction with respect to x times dx. Okay. So this is the net heat flow of our x direction. Using the same principles, we can apply this to the net heat flow of the y direction and our z direction. So the net heat flow in the y direction will be our negative change in heat flow of the y with respect to change of position times our dy, or get rid of this, and then our z direction, net heat flow z direction will be equal to our negative change in heat flow z over change of position times our dz. Okay. So, using this and relating it back to this equation here, we'll get our energy stored, which we said is our density times our heat capacity times our change in temperature with respect to time, evaluated throughout our volume, dx, dy, dz, is equal to our net heat flow. So for our net heat flow, we'll have negative dq for x, change in position, dx, plus we'll get actually rid of this plus. Okay, and then to that we'll add our energy generated, which is heat flow times our throughout our volume. So that's our dx, dy, dc. Because we have a solid cube here, we can evaluate our heat flow using Fourier's law. And we know Fourier's law tells us our heat flow of conduction, which is heat flow is equal to the negative thermal conductivity times our area times our temperature gradient. Okay, so we'll start with our x term. So for this qx term, we'll say Qx is equal to our negative thermal conductivity times our area. So if we are evaluating the area in the x direction, we'll use this surface here. And the area of our surface would be our dy times our dz. So we'll say our negative thermal conductivity times dy dz multiplied by our temperature gradient. Okay, and then for heat flow in the y direction, we'll get our negative thermal conductivity times, for our y direction, since we're flowing this way, we will use this surface, which is dx dz it'll be times our temperature gradient as well. And then finally, for our heat flow z, we'll get our negative thermal conductivity times, in this case, flowing this way, we'll get the area as dx dy. Dx dy times our temperature gradient. Oops. And this should be y. Now, if we write out this whole equation, we'll get our stored energy. So density times heat capacity times our change in temperature with respect to time throughout our area. So dx dy dz is equal to our energy generated, which we said is our heat flow throughout our area, dx dy dz plus our net heat flow. So that would be our net heat flow in our x direction, which we said is equal to our negative thermal conductivity times our area, so our dy dz, times our temperature gradient plus our heat flow in the y direction, so that'll be our negative thermal conductivity. Here, actually, keep these with their respective colors. So our negative thermal conductivity times the area of our heat flow in the y direction, so that would be dx dz times our temperature gradient plus our negative thermal conductivity times area of our z direction, which would be dx dy times our thermal conductivity. Okay. And then this will all be, forgot to include our terms dx dy dz as up here. Okay, so using that, we can cancel all of our volume. So this goes away, this goes away, this goes away. And what we're left with is our energy stored, so density times our heat capacity, multiplied by our change in temperature with respect to time, is equal to our heat flow minus our thermal conductivity minus our thermal conductivity times temperature gradient in the x direction minus our thermal conductivity times temperature gradient in the y direction minus our thermal conductivity times temperature gradient in the z direction. So if we remember to, if we divide this equation by our rho c, we remember that our thermal conductivity divided by our density times our heat capacity is equal to thermal diffusivity. So to simplify this equation further, we'll divide both sides by our rho c. So we'll get change in temperature with respect to time is equal to our heat flow divided by rho c. And we can also bring out our this term throughout for the whole equation. So we'll get, and we'll just call it alpha for simplicity. We'll get our alpha times temperature gradient in the x direction plus temperature gradient in the y direction plus temperature gradient in the z direction. So this will be our equation. If we plug our values from Fourier's law into our equation, we'll get this. Our energy stored, or our density times our heat capacity, multiplied by our change in temperature with respect to time, throughout our volume, dx, dy, dz. Oops. Is equal to our net heat flow. So we'll start with the net heat flow of the x direction, which will be our negative d over dx times our negative heat capacity times our area of the x direction. So that would be our dy dz, or this is negative thermal conductivity. Multiplied by our temperature gradient of the x direction times dx. Plus our negative, for our z term, or y term, we'll get d over dy times negative thermal conductivity times the area of the y direction, which will be our dx dz times our temperature gradient in the y direction times our dy. And then get our negative d over dz times our negative thermal conductivity times our area. So that'll be dx dy multiplied by our temperature gradient z direction times our dz here. And then plus our energy generated, so that'll be our heat flow throughout our area, which is our dx dy dz. Okay, so we can, to simplify this, we could start by canceling all of our terms for volume, because they remain consistent on both sides. And what we're left with is density times heat capacity times our change in temperature with respect to time is equal to our negative d over dx times our negative thermal conductivity times our temperature gradient with respect to x minus that for the y, so d over dy times negative thermal conductivity times the temperature gradient in the y direction, and same with the z, so d over dz times our negative thermal conductivity times our temperature gradient with respect to z, plus our heat flow. Okay, so to simplify even more, if we recall, we know that our thermal conductivity divided by density times heat capacity is our thermal diffusivity, or alpha. So if we divide both sides of this equation by our rho c, we'll be left with our change in temperature with respect to time is equal to, and we'll bring out our thermal conductivity term for each of these terms. So, and we'll just say our negative thermal conductivity, rho c, times negative d over dx dt dx plus negative d over dy dt dy plus negative d over dz dt dz, and that all plus our heat flow divided by rho c. So each of these terms will also simplify into our second derivative. So for example, this one will be it would be negative second derivative of our temperature with respect to our position. So our final equation for three-dimensional heat diffusion will be our change in temperature with respect to time is equal to, we'll say our heat flow divided by our heat flow divided by our density times our heat capacity plus our thermal diffusivity, and here we'll just cancel all these negatives here. Thermal diffusivity times second derivative of temperature with respect to x plus the second derivative of our temperature with respect to y plus second derivative of our temperature with oops, let me use blue for this. Second derivative of our temperature with respect to z. And here's our equation. So to derive the temperature profile of a one-dimensional system, we can use our equation for the heat diffusion equation for our three-dimensional equation. So that was change in temperature with respect to time is equal to our thermal diffusivity times second derivative temperature with respect to x plus second derivative of temperature with respect to y plus second derivative of temperature with respect to z plus our energy generated. Okay, so since this is only one-dimensional, we can cancel out these two terms, and what we're left with will be as follows. And since we're at steady state, we know that this will go to 0, and we'll be left with our second derivative with respect to x plus our heat generation divided by k is equal to, which is equal to 0. So we'll need to integrate this equation twice because we are at a second derivative in order to get our temperature profile. So with the first integration, we'll get change in temperature with respect to position is equal to our negative heat generation divided by our thermal conductivity times x plus our C1. And our C1, we'll say at x equals 0. If we plug in 0 here, our C1 will also be 0 because our change in temperature with respect to x, got a little notification. Our change in temperature with respect to x will be 0. So C1 equals 0. Okay, so to take a second integral, we'll get our temperature Tx is equal to our negative heat generation divided by K times x squared plus C2. Now, at Tx, we'll call this TL. So if this plate is perfectly insulated if the right plate is perfectly insulated and the left plate is losing temperature to air, we'll say that the temperature on the inside is 100 degrees Celsius and the temperature on the outside is 20 degrees Celsius. The temperature at x equals L, so TL should be equal to 20 degrees Celsius. Which is equal to our negative heat generation divided by thermal conductivity times our x squared plus our C2 term. So we can use this to solve for our C2. So what we're left with is C2 is equal to our negative heat generation divided by thermal conductivity times x squared minus 20 degrees Celsius. So with this, we can, and this is actually, x will be specifically at x equals L. So actually, so using this in our equation for our temperature profile, we'll get Tx is equal to our negative heat generation divided by our thermal conductivity times L squared plus our C2 term. So that'll be minus our heat generation divided by thermal conductivity times L squared minus 20 degrees Celsius. And what we're left with, simplifying this down, is this should be x. Our 20 degrees Celsius minus heat generation over our thermal conductivity times x squared minus L squared. It should be 2 after the second derivative, and then plus here. So oh wait, I see what I did. L squared minus x squared. Okay, so our temperature profile will look something like this. At T equals 0, our temperature here, and as we move farther, our slope increases. Let me redraw that. Now, the reason it's a curve is because of this x squared value. The x squared will be parabolic, and it's also negative, so it'll go downward. So as it increases, the temperature profile will, the slope will decrease parabolically. Parabolically. And the reason that the slope continues to increase is because on the right wall, we have 0 heat loss initially because it's perfectly insulated. And as we move farther to a greater length L, we will accumulate more and more and more heat loss. Now this happens because the greater the length, the greater the area will be in the Fourier's law equation, which, if we remember, our negative thermal conductivity times our area times our change in temperature with respect to time is equal to our heat flow. So this area term will increase as our L increases as well. So as it gets bigger, there will be more cumulative heat loss. Okay, so to derive the heat diffusion equation of a two-dimensional surface, we could say our heat diffusion. So we'll use this equation from above. So our heat diffusion is equal to our heat generated plus our thermal diffusivity times our x component plus our y component. And we won't need the z component because we're only in 2 dimensions. Now, the problem also states that we're at steady state, meaning our heat diffusion will be 0 because at steady state, nothing changed with respect to time. It also states that there is no heat generation, so this term will also go to 0. Okay, so if we sketch this out using a grid, and we'll say that each of these squares on the grid will have a length of x equal to delta x and a height y equal to delta y. Oops. And we'll say that the entire height of the bar y is equal to j times delta y, and the length of the bar x is equal to I delta x. So to evaluate the temperature of each of these squares, we'll say that the center square has a temperature of T I J. And knowing that each of the squares is influenced by the temperature of the squares around them, we'll say that the right square has a temperature of Ti plus 1 J. The left square has a Ti minus 1 J. The above square has a temperature of Ti J plus 1, and then the square below has a temperature of Ti J minus 1. So using our finite difference approximation, we know that our equation will be, in our x direction, our x component, so second derivative of temperature with respect to x, is equal to our Ti plus 1 J minus 2 times Ti J plus 2 over, or 2, no, plus Ti minus 1 J, all divided by delta x squared. And then for our y term, we'll get Ti J plus 1 minus 2 times Ti J plus Ti J minus 1 all over delta y squared. Now, since this is a square, we can say that delta x is equal to delta y, which we'll just say is equal to a term delta. So if we add these together, we'll get Ti plus 1 J minus 2 times Ti J plus Ti minus 1 J divided by delta squared is equal to plus Ti J plus 1 minus 2 times Ti J plus Ti J minus 1 divided by our delta y squared is equal to 0. And we could say, actually just say delta. We could say that these delta terms are equal to 0 because the entire equation is equal to 0. So in the end, combining terms, we'll get Ti plus 1 J plus Ti minus 1 J plus Ti J plus 1 plus Ti J minus 1 minus 4 times Ti J is equal to 0. Now we could say that our temperature of the center, our Tij, is equal to all of this plus 1 J plus Ti minus 1 J plus Ti J plus 1 minus plus Tij minus 1 divided by 4. So if we take this over to Excel, and we'll call the top of this square 310 degrees Celsius, the bottom 250, the left side 100 degrees Celsius, and then the right side 200 degrees Celsius. So if we plug in our equation, so we said that the temperature of a square will be equal to the temperature of the left plus the temperature of the right plus the temperature of the above plus the temperature of the below, all divided by 4. And let me put parentheses in here. Okay, but before we can apply this to the entire equation, because the program would be requiring values that don't yet exist, because, for example, the right and the below here don't yet exist. If we go to File, Options, Formulas, and this Enable Iterative Calculations, enable that, and then we'll set the iterations to 10,000. So if we then drag this down, oops. Ooh, let me try that again. If we drag this down, okay, third time's the charm, and drag that across, we could see how the temperature changes throughout the entire surface.